Somehow the music knew it was time to stop so we could begin class. All right, it is 11:30. Good morning, everybody. How you doing? I'm trying something a little bit different with the board setup here. The camera cannot, because it's plugged into this computer here, I'd have to really move everything over to get the camera to face this board. But I want the camera to capture board writing. I think that would be great and easy to do. So what I have here is I have duplicated the video stream onto that board, so you guys can still look up there and see nice and big what I'm writing. But I'm actually writing from way over here at the side of the room. Hello. All right. So we've been doing what this past week? Guys? Anything? Nothing. We've been sitting at home, lying around. No, what have we been looking at? Graphing trigonometric functions, right? Good old sine and cosine. So the one thing I haven't gotten a chance to do is, because everybody was taking this darn AP test, I haven't gotten to show you guys how I graph a trig function. This is the easy peasy lemon squeezy method of making a quick, graph is not the right word, quick sketch. Right? How to sketch a graph. And it always starts with the axes. Right? Actually, it starts with a better marker. Let me see if this one's an improvement. Oh, that's that. Well, it started out nicer. And notice my axes are totally lopsided here. Right? Because when we graph these, we understand that a sine, cosine, and the other trig functions are periodic functions, right? They repeat themselves over and over again. So we only need to capture one part of that repeated segment. Right? And that part usually starts at 0 and goes towards the positive x-axis. So that's why I'm heavily emphasizing the positive x-axis here. Right? Or the theta axis, right, for your angle. Oh, this marker is much better. Okay? Now, by default, there are 4 key points on your x-axis, right? The period of the function. So starting at 0, how far do I have to go until it repeats myself? 1 full revolution around the circle. And that will always be 2 pi until it gets transformed, right? And then we want half that, 2 pi, halfway around the circle. And go ahead and mark the quarter marks as well. So that's pi over 2 and 3 pi over 2. So these all correspond on your unit circle, right, to here, here, there, and there, right? Those are the most important points. Next, scale your y-axis. I'm going to go to 1 and -1. If we're on the unit circle, that's how far I can go. Right? And now we draw in a curve, depending on what curve we want to start with. Sine, okay, starts at 0, has a positive slope through 0. It's going to go up and up and up to 1, meets at maximum at 1, at the pi over 2 mark, comes back down, equals 0 at pi. Continues on through, so we've got a negative slope there. Continues, reaches a minimum here at -1 at the 3 pi over 2, turns back around, goes back up, and repeats that positive slope through 2 pi. So with those key sections in place, now I can just connect the dots with a nice smooth curve, like so. Or, the way I really prefer to do it, is I draw a set of axes. I then decide, hey, what kind of curve am I making? I'm making a sine curve. Sine curve always looks like this. Oh, shoot, I overshot. That's okay. We'll just extend that a little bit. All that theta or x, right? whatever you like, whatever your independent variable is. And now go back and mark, that's 2 pi, this is 1 pi, up here is 1 on my y-axis, and here is -1. That's way easier, don't you think? Do not force yourself to try to fit predetermined axes. Oh, I got to hit this point, but I got to make it curved and bend it like... No. Trust me. A little bit of practice. It is so simple, easy to freehand this curve, as long as you're not trying to force it to any particular spot. When you force it, it looks ugly. I mean, wouldn't you agree this is much prettier curve than this one, right? So start with the pretty curve, then add in, like, think of your axes as annotations to it. Oh, this point is pi. And this point I can find out is pi over 2, and we can 3 pi over 2, right? Add that part in after. It's so much faster and easier. That's hand-drawn sketching. Any questions there? All right. When you're doing this, when you're creating the sketch of a graph, you're not just sketching any old sign, right? You're usually graphing from a function. So what do you do when you're given some other function? This did not erase as well as I had hoped. More elbow grease. There we go. Let's do y equals a times sine of theta over b minus, color code these here, h plus k. I mixed up my caps. Now what have we done to it? We've transformed it. Transformations on a trig function. I can substitute this. This works for sine, cos, tan, etc. We can apply that to any of these. They work exactly the same way as they did for any other function. The same way that this could have been. Now let's get another color in here. Instead of sine, this could be the squared function. Remember when we looked at parabolas? We spent so long on parabolas, right? You can multiply in front, that's a. You can add outside, that's k, right? You can multiply or divide on the inside, that's b. You can add or subtract on the inside, that's h, right? The same thing, the same setup. So you're going to get the same transformations. What does multiplying by a always do? Is it the frequency? No. You're using the trig-specific words. Let's talk general transformations first. If I take the whole function, whatever it was, could have been squared, it could have just been a parabola. So I take my x, I square it, and then multiply everything by 5. It makes everything 5 times bigger, right? All the y values will be 5 times bigger, but the x values weren't affected. So this gives me a vertical stretch by a, right? It's a scale factor. It stretches the whole thing up. I made it taller. I took all the y values and made them bigger. So in the case of trigonometry, now instead of 1 and -1, maybe I go up to 2 and -2, right? It's going to affect my y scale. In fact, we can sometimes refer to this as a scale factor. It's a vertical scale. Scaling, a vertical scaling by A. Does that make sense? Which in trig terminologies means it is the, anybody know that one? So the fancy word for this becomes, starts with an A, ends with a amplitude. So what is B going to do? If A was the vertical scaling, B is going to be inside the parentheses, horizontal. Everything inside is horizontal. Everything outside is vertical. Now I say scaling by B. We divided by B. Because remember, everything inside here is the opposite of what you'd expect. I took all my original x values. Let's pick an easy one, 2 pi. Originally, when I plug 2 pi into sine, I get 0, right? What if b was 2? All right, so here, what is it? Set a equal to, what happens when we set b equal to 2? How does that change the scale? Well, now, 2 pi for theta divided by 2 is what? 1 pi. So now I get the results of putting 1 pi into sine. Sine of 1 pi is, well, okay, it's still 0. But now putting 2 pi in gave me what usually 1 pi results in. Right? In fact, maybe let's think of a different one. What about pi over 2? Right? That way I get a different value. If I plug in pi, but b is 2, I'm actually taking the sine of pi over 2. Sine of pi over 2 is my maximum value. But I put in pi to get the maximum value, so it moves over here. Right? So when b equals 2, my horizontal scaling changes, and now I've stretched it way out there. So I divide by b, but it stretched it bigger. Okay? You get the opposite effect. I divide by b, it makes the x values bigger. I need a bigger x value to get the same effect here. See that? And you can always test a couple points. That's exactly how I worked it out here. Just try a thing. Wait, if I plug this in, it would turn into that number, and the sign of that number is this. And as soon as you've got a point on their plot, you're like, oh, okay, I just got to move it up there. Or the erased version here, right, is you just draw the curve the same way, but you adjust the actual scale, how you label it. Oh, now the maximum is now called pi. Right? Okay, how about H and K? I've got another color here. What do these guys do? They are my vertical and horizontal what's? These A and B stretched it. What do H and K do? They shift it. Excellent word. Yeah, shift. Or the long term would be translation. Right? They translate it. Right? Now, couple things here. K is easy when it comes to the trig values. K is literally moving them. So if K equals 2, instead of going through 0, 0, I now start up here, right? We do that. Shifts it up. Just move the whole thing vertically. Very easy. Horizontally, remember it's negative. Okay? So watch out for that opposite sign. If h is a positive value, that means I subtract a positive value and then they take the sign of that. So if h is positive is pi over 2. Then what happens? Well, I take theta and I subtract off pi over 2. So let's pretend that when I plug in pi over 2, I then subtract that off, I get 0. So I'm taking the sign of 0. Normally the sign of 0 is 0, but that's happening at pi over 2, right? So then it shifts it. Oops, I missed. Like that, right? Shifts it to the right, even though I said minus pi over 2, right? So h is positive, I get a positive shift, but it looks, remember you're always subtracting positive value. If you subtract a negative, then it looks like it's written as plus. Okay? Don't get that mixed up. We've done that all year to every function so far. People will still screw it up. Now, what if h was 2 pi? Would anything actually look different? No. Right? If h is equal to your period, well, it's repeating. What I haven't drawn is the repeated version of the sign, out here. Just moves it all up there. But it looks all the same, right? So you will see no difference. How do you know what your period is? B will tell you you said earlier, your frequency / period. Okay. Frequency is how many cycles do I get between 0 and 2 pi. Period is how much x-axis do I need before I complete one cycle. So it defaults to 2 pi, but it gets divided by whatever b is. Because if b is 2 pi, then I plug in 2 pi. 2 pi over 2 pi is 1. Right? Reduce. B would not be 2 pi. B rarely has the pi's. H has pi's. B usually does not. B will just be some integer value. Or it could be a fraction. Theta divide by 1/2. Right? If b is a half, then you'll see it as sine of 2 theta. Right? Because something divided by 1/2 equals same as multiplying by 2. Right? Don't let that trip you up. Questions so far? No? That's it. That's sketching and transforming trigonometric functions. A lot of stuff that you already knew, just applied to a new shape. In fact, I would say when you're graphing anything, just graph rules. Excuse me, H. 1. Know what shape you're dealing with. This comes from what type of function is it? Is it a sine function? Is it a tangent function? Tangents, right, look like this. Is it a quadratic function? Cubic? Some other polynomial? Right, start with shape. And 2, let's ID the transformations. Okay? So that is, go through the rest of the equation and find, this is vertical stretch by this much, horizontal shift by that much, right? List all those out. Find what moved where, how. And then axes, sketch, and scaling, and labels last for ease of use. Right? And that's it, you're done. 3 steps. Okay, now, I pulled a fast one on you on Tuesday. I got rid of the worksheets for this week. I just deleted it. A couple people had actually finished Monday's worksheet, so sorry about that. I'm just going to do the Desmos. So if you haven't finished the Desmos activity from Tuesday, do so now. If you have, you can relax and work on something else for the rest of class, okay? Friday, we have another Desmos activity. This is the marble slides version. So I think there was actually a couple of those at the very end of Tuesdays. So this will be a full one of playing with, right? Adjust your equation so that you get a graph so all the little marbles go down and collect the stars. I love that game. So we'll just be playing that one on Friday, okay? Cool. How do you think this worked? Was this okay for you guys? See, look up there, but I'm over here. Oh, yeah, that's kind of covering the corner there. Okay. I'll need to block that out next time. All right, there we go.